and very little number of holes. Holes present in N-type semiconductor due to generation of electron-hole pairs mainly caused by thermal excitation. A P-type semiconductor block will have a significant number of holes. And very little number of free electrons. Free electrons present in P-type semiconductor due to generation of electron-hole pairs mainly caused by thermal excitation. Let us create a simple p-n junction diode. Let us join an N-type and a P-type material together. The majority carriers in N-type material are free electrons. The majority carriers in P-type material are holes. Let us see what happens at the junction of these two materials. Adjacent to this junction edge, free electrons in the N-type material will recombine with holes in the P-type material. As a result, there will be lack of free electrons and holes across this region. This region is called depletion region. We know that an N-type material is electrically neutral because the number of free electrons and positive donor ions are same in an isolated N-type material. Similarly, a P-type material is electrically neutral because the number of holes and negative acceptor ions are same in an isolated P-type material. After absorption of free electrons in N-type side of in depletion region, uncovered positive donor ions will remain there. After absorption of holes in P-type side of in depletion region, uncovered negative acceptor ions will remain there. This region of uncovered positive and negative ions is called the depletion region due to the depletion of free carriers in the region. Due to the presence of these positive and negative ions, a static electric field called as barrier potential is created across the junction. It is called as barrier potential because it acts as a barrier and opposes the further migration of holes and electrons across the junction. Now, we connect lead to the ends of each material. We made the basic p-n junction diode. Now, we connect positive terminal of the voltage source to the lead connected to P-type side. And we connect negative terminal of the voltage source to the lead connected to N-type side. In this condition, diode is said to be in forward biased condition. We already told that there is a barrier potential across the junction. This barrier potential acts in the opposite of the forward applied voltage. So, there is no forward current through the diode unless the magnitude of the applied voltage becomes more than that of barrier potential. This voltage we refer as forward biased voltage. For silicon, forward biased voltage is 0.7 volts. For germanium, forward biased voltage is 0.3 volts. If we apply more forward voltage than forward biased voltage of the diode behaves as closed switch. Now it gives rise to an uncontrolled forward current through the diode. There is no more voltage drop across the diode beyond this forward biased voltage. We can only limit the current by connecting external resistances series with the diode. Now, we connect negative terminal of the voltage source to the lead connected to P-type side. And we connect positive terminal of the voltage source to the lead connected to N-type side. In this condition, diode is said to be in reverse biased condition. Due to attraction of positive potential, the free electrons in N-type region go away from the junction, Due to attraction of negative potential, the holes in p-type region go away from the junction. This makes the depilation layer of the junction wider with increasing reverse biased voltage. In this situation, the current does not flow through the diode. This is because free electrons in n-type region and holes in p-type region cannot cross this wide depletion region due to electrostatic force of the applied reverse voltage. As we told earlier, there are always some thermally generated holes in n-type semiconductor and free electrons in p-type semiconductor. We call these charge carriers as minority charge carriers. These minority charge carriers also present in depletion region. Due to electrostatic force of applied reverse biased voltage, these minority carriers will smoothly flow through the diode. Because the polarity of reverse biased barrier potential does not oppose the flow of holes from n-type to p-type region, and free electrons from p-type to the n-type region. As the number of minority carriers is very few, a tiny current flows from n-type end to p-type end in the diode. This current is called reverse saturation current. If we ignore this tiny current, we can say there will be no current flowing through the diode in reverse biased condition. So, we have seen